Yeah, participants, today's session will be conducted by he's segregated from computational biology and bioinformatics, and I hope that you will get the most benefit from his expertise. All the very best. So, please.
Thank you. ये बैठ के रहना है कैसे रहना
It's a free, it's completely
ये लोग पार्टिसिपेंट हैं और
ये सारे पार्टिसिपेंट्स
ऑनलाइन भी
ऑनलाइन ज्वाइन।
लेकिन अगर मैं खड़ा रहूंगा तो वो देख नहीं पाएंगे।
सर आप जैसे भी चाहें, आप जैसे वीडियो ऑफ कर all of you are requested to kindly switch off or put your boards on silent mode and please and keep for using of the computer, right?
Okay, so today we will be discussing about an AI-based platform which basically help in early detection of lung cancer and how it helps in diagnosis and therapeutics. That is the objective of today's talk. I hope my slides are visible to everyone. Okay. So before we go ahead, first of all, we need to understand what are the lung cancer cases which are there in the world. So it is said that lung cancer is one of the most or the second most common cancer in the United States. And of course, in other countries, it is very much prevalent. And one of the major reasons why lung cancer is there in the society is because of the tobacco smoking. And there are variety of lung cancers based upon the histopathology. Okay. The majority of the lung cancers are of non-small cell type, and another type is small cell type. It depends upon the what you see inside the microscope or histopathology slides. So based upon that, the classification has been done. Okay. Now, it is a very dangerous kind of a disease where people die very quickly. There's hardly any time for the patient to take treatment and survive. You can sit down. Okay, so there's hardly any time which is available. So scientists and doctors struggle to save patients. It's not a small viral or something. People die in very few months' time. The person suffers. And who's the famous celebrity who recently suffered from lung cancer? Can anybody name? Anybody who knows a famous celebrity who had a diagnosis of lung cancer? Sanjay Dutt, very good. And could you also now tell me the reason why he had suffered lung cancer? Why he particularly not? He was a chain smoker. I don't know whether he's still taking or not, but he was a chain smoker, and one of the risk factors he aggravated to great extent, and because of that, the mutations happen. And because of that, the lung cancer. Okay, so chain smoking, alcohol, all these factors are important to cause any cancer, especially lung cancer. Now, there are variety of disease treatment which are available, like chemotherapy and radiotherapy and other kind of therapies are available. But these therapies have very less success rate. Okay, people do not get results very easily, and even if the results are there, we are not able to save patients' lives because the cancer recurs, cancer metastasizes. That means spreads to other organs in the body. So that happens very easily, and because of that, it is a very challenging disease to take care. So there's a drug called EGFR, targeted therapy. There are certain drugs which targets EGFR. Okay, that is epidermal growth factors, which when targeted specifically can help to treat this disease effectively. But the problem is each patient has got different mutation profile. You know, a person A would be different from person B. So which medicine to give to A rather than to B, we need to have a genomic sequence of that particular patient. Okay. To do that, we need to have a next generation sequencing. We need to sequence that data. If you want to sequence that data of a patient, that means the mutation profile has to be understood. And you need to spend money and the time has to be spent. Because sequencing is not an easy exercise. It's not a blood test like hemoglobin, which the report comes in few minutes or few hours. So it takes time. You know sequencing, all of you are biotech students. Okay, so the second problem is, especially for the countries like India, the sequencing cost is very high. So patients are not that rich to afford that kind of a diagnostic test. So if you want to screen large number of patients all across India, you need to spend a lot of money to do that. Okay. So how to make sequencing available to large number of people across India or hundreds and millions of people across India as a screening device is very tough. Okay. Secondly, the cost factor, apart from the cost factor, you want to sequence the lung tissue. Lung tissue is inside. It's not easy to take the lung tissue outside your body. You need to put the bronchoscope, put the device over there, and or you need to make a drill over here and take the sample out. The biopsy sample should come out. So that you get the tumor in hand. So how the tumor would happen in your hand? Because you need to, it's a painful procedure. It's like a mini surgery. A surgeon has to be involved. Then you do histopathology, then you do DNA extraction. So it's a long process. And any surgery means a lot of time, preparations, and of course, cost to the patient. And pain also, discomfort. It's not easy to get your chest open. Okay. So then, even if you get the tissue out, you don't know whether you got the right amount of tissue or not. So adequacy of lung cells, the tumor cell has to be there. Because if you don't have adequate tissue, you will not be able to do diagnostics later on. So that means the technology is invasive and it is not cheap, it is costly. Both these problems create problems for clinicians and the doctors. So the idea is to get some non-invasive and low-cost technology available to the patient data sets. And what we did in our lab, collaboration with leading hospital in Delhi, we combined genomics data with PET-CT scan data sets in order to get the answers for these problems. Now you have understood what the problem is, and we worked on solving this problem in our lab. So we took care of problems in resource constrained country. India is a very big country, but there's no paying capacity. Very few people can pay. Okay. So we see there are 130 crore people living in India, but the income levels of most of the people is not that much who can afford such kind of a costly technology. So it's a resource constrained country, number one. Second challenge we face is adequacy of tissue, which I have already told. Then locating the suitable tumor tissue is also a challenge. You know, you have a lung, but where is the tumor? Where is the cancer cell sitting? Locating that is another problem. Then what happens? A person suffer from cancer, immediately start the medicine, chemotherapy. So there's a mutation which changes over a time. The moment you give chemotherapy, the DNA also mutates. Not because of disease, but because of the treatment which you are taking. There's a shift in the treatment. So what you are treating will change over a period of time. Further, the DNA quality also reduces. And currently, the existing technologies have only focused on detection of nodules in CT imaging. And what we found, the data which is available in literature was majorly focused on Chinese and white population. There was no study which was done on Indians. So that is a unique study which we conducted in our lab, which were focused on Indian patients. So that was one of the strengths for our work. So data was India. So then we did a little bit of literature survey also. And we found that there were some papers, some authors which have worked on automatic detection of lung nodules, where they combine artificial intelligence and CT scan. But nobody had combined the genomic data. Only they worked only on CT scan and artificial intelligence. So what we brought in another set, that is the genomic data in the equation. Suzuki also worked in 2003. They made some computer programs to detect lung nodules. Lung nodule is nothing but your lung cancer in low dose CT scans. They also, some recently this year only, when they try to combine EGFR genotype, that is the genomic data, versus lung cancer patients. So little bit information is there that has come recently. By the time we were working, they were also working. So first of all, what we did in order to execute this study is we collected data sets, and we call these data sets as 5 data sets. We call them cohorts. Cohorts is a collection of patients. The first cohort had 1300 plus patients, number 1. Okay. And they were collected from a daily-based hospital, it's a oncology hospital. In this cohort, all these patients were Indian. Their ethnicity was Indian. And they were from 23 to 92 years of age. The mean age of these patients was 62. In cohort 2, we had 591 patients, again Indians, all Indians. The mean age was 61. The third, again, Indian group, Rajakshi. The third cohort is again 96 patients. The mean age was 58 years. The fourth cohort were all whites for comparison, 211 patients. The mean age is 67.96. Cohort 5, again white and Chinese, 1000 plus patients, which we took it from internet. Then we collected, these were the patients, then we collected data from these patients from 2015 to 2021. Our clinical collaborator got this data. And we collected the CT scans from these patients. And since the CT scans were done by different companies, scanners, one was GE Medical System, second is Philips and Siemens. These are the image files we got of these patients, the cancer patients. Since they were scanned from different companies, so we have these numbers, we have this information available. So this is the overall workflow for the study which we conducted. First, we collected the data set from TCIA. And we made a model which we acronym as AI-based predictive system. In subsequent part of my presentation, I will be using AIPS to determine this. AIPS means artificial intelligence based predictive system. Then we added a letter called N. If you see AIPS N. Okay. And we also added a letter called M in that system. N means we are trying to build up the models, the machine learning model based upon the data. So here we took the information from various cohort which I just described, 1 to 5. Okay. So here I took cohort 1 to 4. Cohort 1 to 3 was India. Cohort 4 and 5 were all foreigners, non-Indian. So what we did, we took the training data set. What was the training data set? The images, the CT images, PET CT images, which were annotated by the radiologist. What is the meaning of annotation? No. The radiologist has defined, this is my lung, this is the tumor, this is the size of the tumor. All the details of the tumor was presented to us. Okay, because that is very important. Unless we have the information, our machine is going to have a lot of difficulty to learn. Is that clear? So we inputted these CT images with annotation. You have image of the patient, you have the annotation. We trained them using lung segmentation. Segmentation means we divide, it's a big image, right? So there will be lung, there will be heart, there will be bone, there will be, other stuff available. We need to first segment it. Segment it means divide it into different categories. And then out of the segmented picture parts, there will be one part that will be cancer, the nodule. Okay, so first we segmented, then we looked at the nodule. And then we had the annotation. And then we had the machine learning algorithm which learned, this is the nodule, these are the properties based upon the annotation. So it started learning. So the neural network started learning about this whole story. Okay. Based upon that learning, we made the model file. And based upon that model file, we had some scores. And then we proceeded further, which I'll explain it later. In brief, I'll just tell you, the data was collected from TCIA. Then we had the segmentation. Then we had the nodule feature prediction. Nodule feature means whether the nodule is irregular, what is the size, what are the malignancy properties, okay, what is the translucency. Okay, all these features were also studied in detail and we built the machine learning system. And then we did a lot of other activity, which I'll explain a little bit later on. So how did we make, so this is more detailed version. So we call this as AIPS -N is an N stands for nodule. N stands for nodule. So what in the beginning we are focusing on nodule prediction. Okay. Secondly, we were now, we need to start, we do a pre-processing of this images these images are generally in the three-dimensional DICOM format. So it's not like this. Marker है? Anybody who's getting? So normally, image like in your phone, what you see is you take a selfie, you get a 2D image, two-dimensional image, which has x-axis and y-axis. अभी ध्यान देना So normally a image has 2D. In your phone, what you have is a two-dimensional JPEG, GIF. Similarly, there's a format in medical side is called DICOM. That's an acronym or something. Okay. So now in CT scan, what we are working is a three-dimensional, not 2D. It's a 3D image. That means it is like this. Are you getting my point? In this image, there is a tumor. Okay. Now, how will you see this 3D image? Because once you get the image, have you seen X-rays or CT? X-ray देखा है? वो तो ऐसे ही होता है ना, right? लेकिन अब 3D कैसे बनेगा ये? तो हम लोग क्या करते हैं, इसको स्लाइस करते हैं. ठीक है, तो एक्सरे तो एक ही देता है या दो देगा ज्यादा से ज्यादा एपिजेक्टल, पर जब सीटी की इमेज आती है वो स्लाइसेस की फॉर्म में आती है. स्लाइस समझ गए? एक देखा है, जैसे ये एक 3D ऑब्जेक्ट है, उसको यहाँ ऐसे छोटे छोटे टुकड़ों में ऐसे काटना चाहिए. तो जो आपको दिखेगा वो उसके टुकड़े दिखेंगे. पहले ये टुकड़ा, then this one, then third one, then fourth one. Okay, so all these slices will be shown to the patient or a doctor. And because of that slices, you reconstruct the whole story in your brain or in your computer. Are you getting my point? So the image processing will be little difficult here. It is not a normal image processing. What you are getting is a 3D stuff, because my whole lung is a 3D. It's not a, kind of one side kind of thing. And what I'm getting the slices like this, slice like this. Okay, these kind of images will be there. So I'm getting a top view. ऊपर से दिख रहा है मुझे. ठीक है, उसके अंदर ट्यूमर है. अब एक स्लाइस आया, उसमें ट्यूमर इतना सा दिखा. उसके नीचे गए तो ट्यूमर दूसरे स्लाइड में थोड़ा बड़ा हो गया. क्यों? ट्यूमर ऐसा है ना, पहले तो ये दिखेगा, then I see this one, second image पे, then I see this one. तो जैसे जैसे स्लाइड आगे जाते जाएंगे, ट्यूमर will become bigger, and moment I come down, ट्यूमर will start becoming smaller, and then एक पॉइंट आएगा जब ट्यूमर दिखेगा ही नहीं. जब मैं यहाँ आ जाऊँ, there is no tumor. Then there I'll see some other lungs or something. Is that clear? So remember, the problem which we were facing is not a standard problem. It's a three-dimensional thing which we need to work on. Number one. So there are 3D DICOM images which were given to us. So there will be many 100, 200 images होती है एक पेशेंट की. एक नहीं होती. जैसे एक्सरे जब आप लेके आते हो डॉक्टर के पास, आप वो पिक्चर लेके पहुंच जाते हो. यहाँ पर ऐसा नहीं होता. यहाँ पर क्या होगी, 150 इमेजेस है तो 150 फोटो नहीं करता, वो छोटी छोटी पिक्चर्स बना देते हैं. पेट सीटी या सीटी स्कैन जब देखोगे बहुत सारी इमेजेस लगी होगी, तो जरा ध्यान से देखो. जब मल्टीपल इमेजेस, राइट, और उसको आपको वो सीडी में दे देगा और इट विल बी ईमेल्ड. एंड एक पेशेंट का डेटा विल बी huge, 1 GB, 2 GB. ठीक है, एक्सरे कुछ MB में कवर खत्म हो जाता है, लेकिन PET CT एक पेशेंट के लिए भी लॉट ऑफ। अब हमने करना क्या है इसके अंदर, वी नीड टू डू प्री प्रोसेसिंग। ठीक है, प्री प्रोसेसिंग मतलब इमेजेस को डिफाइन करना है, कुछ चेंजेस लाने हैं जिससे वो इमेज थोड़ी सी बेटर हो जाए। And there are different strategies which I will not go in detail because we lot of problem in that understanding. Secondly, हमने क्या करना है, प्री प्रोसेसिंग हम स्टैंडर्ड होता है कंप्यूटर विजन में, हमें प्री प्रोसेसिंग करती है। सेकेंडली हमने क्या करना है, हमने एनोटेशंस को पार्स करना है। वी नीड टू एनोटेट द, वी नीड टू पार्स द एनोटेशंस। व्हाट वाज द एनोटेशन आई जस्ट डिस्क्राइब्ड? इट वाज द इंफॉर्मेशन, what is the size of this tumor, what is the malignancy, okay, and sphericity, speculation, स्पेकुलेशन मीन ट्यूमर के ऊपर इस तरह के स्पेकुलेट होते हैं, कैंसर की ये प्रॉपर्टी है। वो स्फेरिकल है या इरेगुलर है? नॉर्मली जो कैंसरस होते हैं वो इरेगुलर से होते हैं, रफ से। उसमें नॉर्मल ट्यूमर्स होंगे, बिनाइन होंगे, वो गोल गोल से होंगे, स्फेरिकल टाइप की होती है। So we did these kind of a thing. Just a sec, my laptop charging is going down. Give me a second. So every slice had a annotation. Annotation क्या थी? Lexis के साइज की बात करते हैं या उसकी स्फेरिसिटी की बात करते हैं, तो एक इंफॉर्मेशन x, y, z स्फेरिसिटी। ठीक है, ये एक इंफॉर्मेशन अवेलेबल है मेरे पास। Then we talk about size. Let's say K, then malignancy. We have L, M. You know, some numbers, some information is available. Is that clear? So what we had, some information available for each tumor, for each of this image. ठीक है, ये numbers हमें किसी फाइल में पड़े हुए मिलेंगे. We will get these information somewhere. So this is called annotation information. So now what I need to do, first of all, I need to read this information. I need to read this information in context of this image. ये ट्यूमर है और ये इंफॉर्मेशन है, ये ट्यूमर है, ये इंफॉर्मेशन. Is that clear? So every patient's tumor will have some numbers associated with them. That is present in the annotation file. Then we will parse these annotations using a specific library called PYLIDC. PYLIDC. LIDC library को use करके we will be parsing this information. Parsing means reading, understanding, storing, and analyzing that. PYLIDC. And once I read through, because doctor will write in his own way, radiologist will write in his own way, in his own format, I need to bring it to the language or the format which machine, my algorithm is going to read. So I call this format and save that. So one of the format which is associated with these images called JSON format. JSON. Okay. So first thing is we need to understand these formats. Because unless we have the format or information ready, you cannot train your machine. So that is very important. Then third thing what we did was we extracted region of interest. You can see on the picture, region of interest, ROI. ROI. How many of you have used phone camera? How many of you can use phone where you can actually have some value or how many one. Okay. Recognize how does he know your day? And वो ठीक से recognize करता है या नहीं कैसे करता है? Sorry. It is reading the face. ये जब face होगा तो उसके certain features होंगे. नोज होगा, आईज होगी, वो सब होगा. ठीक है. उसको कैसे पता लगा कि नोज आईज होते हैं? तुम्हारे फोन में तो ह्यूमन नहीं है, उसको कैसे पता लग रहा है? We have already trained our algorithm. जो तुम्हारे उसमें लोडेड जो ऐप होता है ना, उसके अंदर लोड होके आया होगा. We have already trained. So one of that algorithm, ये जो फीचर वाला होता है, it's called Detectron 2. Detectron 2 एक एल्गोरिथम बनाया गया जिसको ट्रेन किया गया ऑन ऑब्जेक्ट रिकग्निशन. मतलब किसी भी चीज को रिकग्नाइज कर देते हैं और उसको सेगमेंट कर देते हैं, तोड़ देते हैं. ठीक है. तो पीपल हैव मेड सच लाइब्रेरीज. में से एक फेसबुक की भी टीम थी जिसने अपनी एक बनाई विच दे कॉल इट एज डिटेक्ट्रॉन 2. तो तुम्हारे फोन पे भी जो है वो डिटेक्ट्रॉन 2 नहीं है, बट कुछ और एल्गोरिथम होगा. इट कुड बी VGG. ठीक है. तो ये लाइब्रेरीज लोगों ने पहले से मॉडल्स एल्गोरिथम्स पहले से बना दिए. कैसे बना दिए? they collected all images and their annotation. They collected all the images of your red light, tube lights, your phones, humans, birds, all animals, roads, cars. It's a massive exercise which people have done, and they made a benchmark data set. Based upon that benchmark data set, they designed their algorithm. So they became so powerful, they started detecting the objects automatically. But prior to that, they did all these exercises of collecting data and analysis. That is very important. Based upon that, several research groups have worked, and one of that group was Facebook. They also are scientists like us. और ये कहाँ सबसे पहले फेसबुक ने यूज किया था? फ्रेंड्स आइडेंटिफिकेशन। तुम लोग इमेज डालते थे, तुम्हारा नाम आना शुरू हो जाता था। हाँ ये फीचर अभी है, पता नहीं, मालूम नहीं है, बट पहले बीच में आया था। You upload your image or you're trying to take a photograph, automatically तुम्हारे नाम के आगे तुम्हारा नाम फेस के आगे नाम लग के आ रहा है। तुम्हारे फ्रेंड्स के भी अगर 10 लोगों ने सेल्फी ली हुई है इकट्ठी, तो सबके नाम ऑटोमेटिकली लग के आ रहे हैं। किधर से आ रहे थे? फेसबुक को कैसे पता तुम्हारे दोस्त का नाम है? चलो तुम्हारा पता हो सकता है तुम्हारे प्रोफाइल से, तुम्हारे दोस्त का कैसे पता लगा तुम्हारे ग्रुप के अंदर? लेकिन उसको मैंने बताया तो नहीं कि फोटो तुमने ली, उसका प्रोफाइल कहीं हो रहा है, लेकिन उसने नाम सही बता रहा है। वो कैसे पता लगा? वो क्या करता था, तुम्हारी सारी इमेजेस, तुमने अपनी फोटो डाली, तुम्हारे प्रोफाइल के साथ कनेक्ट होगी। तुम्हारा नाम क्या है? वंश का जो प्रोफाइल होगा, वंश की फोटो लगाएंगे, वंश के साथ कनेक्ट होगी। तुम्हारा नाम जान ने अपना प्रोफाइल बनाया, उसके प्रोफाइल। अब ये दोनों मिलेंगे, पार्टी की इन्होंने आपको फोटो में दोनों ने इकट्ठी फेसबुक पे अपलोड कर दी। फेसबुक के एल्गोरिथम में सर्च, इसने इसका भी प्रोफाइल लिख किया, इसका लिख के ऑटोमेटिकली उसके नाम सर्च कर दिया। ठीक है, उसने ट्रेनिंग की हुई है ऑलरेडी, ये सब काम करती है। तो उसी तरह के एल्गोरिथम का एक नाम है डिटेक्ट्रॉन 2, जो फेसबुक ने अपने ही काम के लिए लगाया था। हमने उसको ट्यूमर के लिए लगा दिया कि भाई अब तो ट्यूमर का काम है। और उसका नाम है, इसका एल्गोरिथम का नाम है, स्पेसिफिक जो नेम है, फास्टर RCNN R101 FPN 116। ठीक है, ये उसका स्पेसिफिक नाम है, बट मोटा मोटा यू कैन ऑलवेज से इट्स अ डिटेक्ट्रॉन 2 एल्गोरिथम। ठीक है, फेसबुक ने कैसे बनाया था ये एल्गोरिथम? इसने कॉन्वोल्यूशनल न्यूरल नेटवर्क बनाए थे। जो लोग मेरे साथ कोर्स कर रहे हैं, दे विल एप्रिशिएट, इट्स अ कॉन्वोल्यूशनल न्यूरल नेटवर्क, CNN। उसका एक वेरिएंट है फास्ट R। ठीक है, उसका वेरिएंट होता है। अभी ये टाइम नहीं है कि हम उसकी डिटेल में जाएं, बट एज्यूम एक कंप्यूटर विजन एल्गोरिथम है जो डिटेक्ट्रॉन 2 नाम से बना है, और उसको मॉडिफाई किया गया, बनाया गया, और उसके बेसिस पे फेसबुक ने अपनी प्रॉब्लम सॉल्व की। हमने क्या किया? वी ब्रॉट दिस एल्गोरिथम एंड लाइब्रेरी इन आवर सिस्टम टू सॉल्व आवर प्रॉब्लम ऑफ ह्यूमन आइडेंटिटी। इज दैट क्लियर? तो ये जो आपको ये येलो बॉक्सेस दिख रहे हैं, ठीक है, these yellow boxes are supposed to detect lungs for me. Chest, इसमें हमें क्या क्या दिख रहा है? We are getting lungs, we are getting heart, we are getting backbone, we are getting front portion of the chest, we are getting the back portion of the chest. ठीक है, वो दिख रहा है स्लाइस हमें। So this yellow box is actually giving me only lung, because I don't want to focus on my hands and shoulders and whatever. I just want to focus on my lung region. That's it. Then what I did, I applied a technique called windowing. Once I detected that this is my lung and I want to discard everything else, now I want to focus on removing the noise. जैसे अभी क्या होता है, when I am taking this lecture, people start talking. ठीक है, आपस में बातें शुरू कर देते हैं। What I do, I come back और चुप करा देते हैं। What I am doing actually, I am suppressing the noise. तो इसी तरह से मशीन को भी नॉइज को सप्रेस करना। ठीक है, क्योंकि नॉइज होगा तो आप मेरी बात नहीं सुन पाएंगे। Similarly, machine will not be able to identify tumor if there is a noise in that. So image की में जो noise है, we have to suppress. Then we need to remove irrelevant bright intensities. अब जो ट्यूमर होते हैं ना, उसकी इंटेंसिटी काफी अच्छी होती है। ठीक है, लंग्स देख रहे हो ब्लैक ब्लैक से हैं, लेकिन ट्यूमर जो है वाइट सा ब्राइट सा है। लेकिन अगर बोन को भी देखोगे ना इमेज में, वो भी बड़ी ब्राइट सी होगी। तो हमारी मशीन फिर कंफ्यूज हो जाएगी कि ब्राइट इंटेंसिटी वाली कहीं ट्यूमर तो नहीं है कहीं। तो उसको पहले ही हमने फिल्टर कर दिया, भाई जहां जहां बोन है उसको हटा दो पहले से, बेकार में क्यों टेंशन लगी। इज दैट क्लियर? तो हमने इररिलेवेंट ब्राइट इंटेंसिटीज को हटा देना है। वो किधर है? वो उनके अंदर दिखेगी, कुछ एयर पॉकेट में दिख सकती है, वो कुछ आर्टिफैक्ट हो सकते हैं। वी नीड टू रिमूव दैट, सप्रेस द नॉइज, फिल्टर इट आउट। So this technique is called lung windowing. तो जो हमारी जो इमेज होगी वो चेंज हो जाएगी। देखो लेफ्ट और राइट में फर्क आ गया, ठीक है। तो फोकस बना रहा हूं मैं अपना। अभी बोलते हैं ना व्हेन वी आर रीडिंग, व्हेन वी आर स्टडीइंग, फोन को स्विच ऑफ कर दो। अभी मेरे फोन मेरे उस पे चल रहे हैं, ये तो बजते जाएंगे, घटाघट बज रहे होंगे पीछे से। नॉट फोकसिंग, क्योंकि अभी मेरा फोकस क्या है? लेक्चर। तभी तुम्हें समझ आएगा, तभी मेरा दिमाग चलेगा, तभी मैं भी समझा पाऊंगा। इस तरह से मशीन को भी हमने फोकस देना है। इज दैट क्लियर? तो मशीन भी ह्यूमन की तरह ही चलती है, मशीन कुछ अलग नहीं है। मशीन जो ह्यूमन सोचते हैं वही है। अगर अभी मेरे फोन बजे और मैं फोन भी आंसर करूं, मेरे दिमाग से निकल जाएगा थॉट प्रोसेस, मैंने पढ़ाना क्या है या मैंने दिखाना क्या है। इज दैट क्लियर? सिमिलरली वी हैव अप्लाइड एंड वी हैव चेंज्ड। देखो शुरू में बहुत ज्यादा नॉइजी था, अब धीरे धीरे सिग्नल बढ़ता जा रहा है, पीपल आर गेटिंग मोर इंटरेस्टेड, वो चीजें थोड़ी सी बेटर होती जा रही है, ठीक है। लर्निंग कैपेसिटी बढ़ती जा रही है। तो सिमिलरली विंडोइंग में क्या कर रहा हूँ मैं, अपनी मशीन की लर्निंग कैपेसिटी बढ़ाने वाला हूँ सब्सिक्वेंट स्टेज। तो दैट इज व्हाट इज हैपनिंग। Then we need to understand, I was talking about 5 features. I discussed there's a sphericity, there's a margin, there's a texture, there's a malignancy, there's a speculation. मैंने बोला था कोई नंबर होते हैं, स्पेरिसिटी का नंबर होगा कोई। स्पेरिसिटी नंबर क्या है? कि कितनी तरह की हो सकती है। लीनियर हो सकता है, लीनियर मतलब सीधी सीधी लाइन में स्फेरिकल। ओवॉइड हो सकता है, ओवॉइड कम लीनियर हो सकता है, राउंड हो सकता है। तो हर एक फीचर के बेसिस पे उसको स्कोर दे दो। अगर वो लीनियर है, गिव अ स्कोर ऑफ 1। इफ इट इज अवॉइड स्लैश लीनियर, गिव अ स्कोर ऑफ 2। If it is avoid only, give a score of 3. Okay. अब मार्जिन की बात करते हैं हम लोग। ये ट्यूमर है, इसके मार्जिन देखते हैं। अगर ये ट्यूमर ऐसा है, इसका स्कोर होगा 1, लेवल होगा पुअरली डिफाइंड, कोई मार्जिन ही नहीं है, सब पहुंच पहुंच। ऐसा है थोड़ा सा, इसको स्कोर 3। और शार्प मार्जिन है, एकदम क्लियर कट आ रहा है, उसको हम देंगे स्कोर ऑफ 5। इज दैट क्लियर? उसको क्या स्कोर देना है, ये नंबर्स के अंदर आएगा, ठीक है। ये अब स्कोर हमने कैसे डिफाइन किए? दीज आर द स्कोर्स व्हिच हैव बीन डिफाइंड बाय द टीम ऑफ रेडियोलॉजिस्ट। So similarly, speculations, textures, and other things are there. Then we build a model, a machine learning model. Okay. So we build this model. Now we know these models have certain layers and other things. Left hand side में देखोगे input image है, देख रहे हो लंग की इमेज दिख रही है एकदम एक्सट्रीम लेफ्ट में। अब बीच में जो दिख रहे हैं जो वर्टिकल लाइंस है, ये सारे क्या है? हमारी मशीन्स हैं। एक नेटवर्क है जो इस इमेज के पिक्सल्स को रीड करते हुए जा रहा है, ठीक है। तो उसका एक बैकबोन हमने नेटवर्क बनाया और उसके अंदर हमने एक सिस्टम बनाया, एक आर्किटेक्चर बनाया कि इस इमेज को कैसे पढ़ना है। और ये इंस्पायर्ड था हमारे फेसबुक के डिटेक्ट्रॉन 2 मॉडल। उन्होंने एक आर्किटेक्चर बनाया था, हमने सिमिलर आर्किटेक्चर को यूटिलाइज किया अपने काम को। Is that clear? Then we tune the hyperparameters. तो हमने hyperparameters होते हैं which are utilized to tune our machine learning system. So we had parameters that how many GPUs will be used, how many threads will be used, how many images will be studied per batch, what will be the learning rate, and at what speed our system is going to learn, how many iterations you will take during the learning, how many classes you will take. All such parameters we defined, and below these parameters we have the specific functions or methods which are utilized to study these parameters. ठीक है, इसको ट्यून करने हमने. So there is a detectron 2 library. फिर उसके अंदर एक क्लास होगी, फिर उस क्लास के अंदर एक मेथड होगा, फिर उस मेथड के अंदर कुछ और होगा. ठीक है, वेरिएबल होगा, फिर उसकी प्रॉपर्टीज होंगी. वो सारी हमने यहाँ पर दिखाया हुआ है. यहाँ पर सॉल्वर, ये CFG नाम की एक क्लास के अंदर सारी चीजें. ठीक है, CFG ये इसने दिया हुआ है फेसबुक वालों ने. अब हुआ क्या, when we did all this training and all, what we got, our program was able to detect tumor very nicely. And this red bounding box and this green box, both are able to detect their respective tasks. They are able to execute their respective tasks. This red bounding box is able to detect this tumor very nicely over here. So you can study the malignancy, you can study the sphericity, you can study the speculation, you can study the texture of the tumor using our program now. Okay. Then next step, as I was telling you, we need to integrate the genomics data. So we brought in another artificial intelligent predictive system where we brought in the mutation information, and we call that program or that system as separate from A and N. N was your nodule. This is your mutation. So here's a nodule, here's a mutation. Now I need to integrate those. Mutation is a separate machine learning system. Nodule is a separate machine learning system. Nodule we worked on using the Facebook detectron 2 computer vision models, and M is the mutation thing. That is a separate machine learning system. Here we did not use the computer vision. Why? In M we did not use computer vision because there was no imaging data. We were working on clinical data. So we utilized multiple machine learning models such as support vector machines, random forest, decision classifier, grid search, random search. All these algorithms were used to build up these M model. Then we integrate those. We combine those models. And now we have the performance. Then we tested those models on certain data sets. And what you see on the graph are the performance metrics. So we studied AUC, we studied F1 score, we studied accuracy, we studied precision, we studied recall. These are all standard parameters to evaluate the performance of machine learning systems. Like you people, whenever you give exam, you are giving CGPA percentage or something. Similarly, our machine learning systems are also given similar kind of scores. Higher the scores are, we declare that person as intelligent or topper. Poor the scores are, that person is classified as duffer, non-performer. Okay? And we tell them to repeat the semester. That's what happened. Same way in machine learning, we have the scores parameter to tell whether your program which you made was correct or not, whether it is performing well or not. So all these parameters like F1, AUC, that is area under the curve, or accuracy parameter tells whether your system is performing but well or not. So what we did, we tested our system, AIPSM model, different algorithm. As I told you, we employed different algorithms like support vector machine, random forest, XGBoost, randomized search, grid search. And once we did that, most of our algorithms are performing beyond 85-90%. Some of them are performing below 75%. So what we did that we found that grid search was performing at 90%. So comparatively it is better. So let me just select this. Okay. That was the logic behind that. Similarly, we did for different cohort. We started our talk with cohorts. We trained on cohort 1 and tested on cohort 2. We trained on cohort 3 and tested on cohort 1. Similarly, we did all these, cross comparisons and all. And all these slides, which I'm going to, mention right now or show right now, will have those parameters. Which cohort, which model was performing well. Is that clear? We trained on Indians, we tested on whites. We trained on whites, we tested on Indians. Is that clear? So all these slides talk about that. And here we are getting performance matrices of AIPS N module, that is nodule detection. And we were getting very good accuracy of 90% of them. So based upon this, now we want to conclude. We started with the problem. What was the problem? We need to put needle to take out the tumor. The cost of sequencing is very high. Patient becomes pain, and patient feels pain. You don't need to do surgery. So we need a technology which is low cost, which is non-invasive. So what we build is a non-invasive technology. That means you just have to take the PET CT scan. You don't have to put the needle. You don't need to do the sequencing. We were able to correlate the imaging data versus genomic data. That means given this feature, this will be the mutation N1. Given this feature, then the mutation will be N2. So we trained our system. Now it is able to detect. By just giving the image data, you will be able to predict what is the mutation inside the patient. Once you have done that activity, now you don't need to do the invasive activities. You don't need a surgeon. You just take a PET CT scan, which is very easy. Go there in the diagnostic, take the picture. Based upon the picture, we are able to tell you whether one mutation is there or second. And what will happen once you identify these mutations? Because of this mutation information, the doctor is able to give you right medicine. Because if you have M1 mutation, you are giving X1 medicine. If you have M2 mutation, you will be giving X3 medicine. That is more suited for you. Is that clear? So that was a problem we started off with. And now we have solved that problem. How we solved? Using image data from the patient, using mutation data from the patients. And then we combined it using two different type of strategies. One was the computer vision algorithms, electron 2, and the second is the clinical information, mutation information using support vector machine and grid search algorithm. We combine different algorithm strategies to solve a clinical problem. Okay, now the system is online, people can use it, and now we want to scale it up. Okay. So this is all for today. So these are some of the papers which we are working on. Some of the papers are published, some are going to get into press very soon. So that's all for today. Any questions? First, I'll take the online question, then I'll take the questions from the audience which are there in the room. Any questions from the participants who have joined online? You can put it in a chat box. Any questions? Okay, there are no questions in the chat box. Any questions from the audience who are there in the समझ नहीं आया? लोग एसेट से हैं कंप्यूटर साइंस के कितने लोग उसमें भी है ठीक है अब हम क्या करेंगे वी विल गिव व्हाट इज द टाइम नाउ ये लोग ऑनलाइन ये सारे खुद भी है या बाहर का भी लोग तो कल एक लिंक दिया था ना फेसबुक के टेक्सॉन टू वाला जो एक तुम थे क्लास में यस क्लास में question is whether ये लोग भी कैसे वो कल जो लिंक था ना वो डिटेक्टर 2 वाला एक
ट्यूटोरियल वाला
हाँ वो जरा इंटरव्यू ग्रुप है
मैं फॉरवर्ड कर देती हूँ।
उस ग्रुप में डाल दे
आपके पास है
नहीं नहीं जूम में रहेंगे ये देख नहीं पाएंगे
अच्छा जूम पे रहेंगे
His question is whether we have implemented a clinical data resolve clinical data हॉस्पिटल से भी काम कर रहे हैं ये जो प्रोजेक्ट था वो डॉक्टर से लिया था हॉस्पिटल ने लिया था मेरे घर से पता नहीं है उनकी प्रॉब्लम थी ठीक है अब करना क्या है नेक्स्ट का जो लोग एंथुसियास्ट है they can help us to scale to reach to other hospital ने एक हॉस्पिटल को टारगेट कर दिया है we want volunteers who can help us to deploy to other hospitals ठीक है आपको ये टेक्नोलॉजी को वहां तक डिप्लॉयमेंट से लेके जाना है डॉक्टर से बात करना है ऑनलाइन किसी पेशेंट का डेटा तो टेक्निकल भी हेल्प कर सकते हो लाइक एसेट पीपल एंड जैसे हमने इलेक्ट्रॉन ट्यूब लगाया मैं बीटीटी लगाना चाहता हूं मैं और फीचर डालना चाहता हूं अच्छे फ्रंट एंड में काम करना चाहता हूं तो दैट इज द इंप्रूवमेंट ऑफ माय प्रोडक्ट नंबर 1 और क्या कर सकते हैं बायोटेक वाले डेटा कलेक्शन में हेल्प कर सकते हैं बोला डेटा इज वेरी इंपॉर्टेंट वी कैन कोलैबोरेट विद डिफरेंट हॉस्पिटल एक बच्चा अगर एक हॉस्पिटल से भी डेटा ले आता है तो अगर हमारे पास 40 बच्चे हैं तो हमारे पास 40 हॉस्पिटल से हम डेटा ले आएंगे तो हमारा प्रोडक्ट और ज्यादा स्ट्रांग होता है ऑल ऑफ यू आर इंटरनल स्टूडेंट so that is a kind of open option for you those who want to take this further scale it up further you are welcome to work with us इसमें कोई आना नहीं होता हफ्ते में एक बार 10 मिनट 15 मिनट के लिए आना होगा ऑनलाइन आप काम कर सकते हैं टेक्निकल काम भी हो सकते हैं नॉन टेक्निकल भी all of you will get certificates will get internship option either with us or our hospital partner okay but technology को हम pan India roll out करते हैं हम आगे बढ़ रहे हैं तो हमारे उसने रेडी बना दिया भूल गए नहीं तो further next project planning that is one project which is available if you find it interesting we can go to different hospitals which we will eventually do अभी धीरे जा रहे हैं those who want to work with us well more than welcome okay रूम नंबर 316 है वहां पर आके इसी मीटिंग में वहां पे बात कर सकते हैं जितना टाइम हो यू कैन वर्क एट कम्युनिकेट दैट इज वन ठीक है एआई में भी ट्रेनिंग मिलेगा ये कैसे किया इसके ऊपर हैंड ऑन ट्रेनिंग करनी है इसी तरह कहीं और समझेंगे नंबर 1 तो क्या कर सकते हैं
हम भी बोल कि डेटा से काम हो करें डेटा मेरे
हाँ तो अभी इसको और रोबस्ट बनाने के लिए हम इसको अब जब नया डेटा लेके आओगे तो दोबारा से ट्रेनिंग किया जाएगा दोबारा से टेस्टिंग होगा कहीं भी आप अपने डेटा पे काम कर सकते हो सीख सकते हो गाइड फ्रॉम जाऊंगा तो आई थिंक आई हैव आंसर्ड योर क्वेश्चन यस वी डिड इट इन द वन ऑफ now want to go to more questions so he is asking whether it's the first time somebody has applied in this kind of problem yes it is the first time but again lot of novelty can be done you can work on getting new addresses अभी तो हमने एक ही है इसको भी टाइम इंस्टेंट तो बैठ के उसके साथ काम करना पड़ता है ये नहीं कि हमने सोच लिया तो सही हो गया कुछ महीने लग जाते हैं उसमें बैठ के तसल्ली से काम करना पड़ता है अभी क्या करेंगे ये तो पूरा नहीं सिखा सकते बेटे टेक्नोलॉजी टूल का थोड़ा सा हैंड्स ऑन बोला है कि ऊपर वो लिंक आ चुका है लिंक भेजिए
यू कैन चेक योर व्हाट्सएप
तो आप अपना वो शुरू करें उसका हैंड ऑन कर दें ये तो है लंबा काम है टेक्नोलॉजी पर उसकी टेक्नोलॉजी पे काम है लिमिटेशन क्या है? में से इंडिया हमारे किया था कोई भी न्यूज़ है एएलपी का नहीं करते वो न्यूज़ पे काम करने मुझे तो ये लिमिटेड सेट ऑफ केसेस इसको क्लाइंट के कस्टमर होंगे यही टेक्नोलॉजी ना कर फिर इसको देखते हुए हमारे पास एक एम्स और पीटी फॉर्म में बहुत बड़े बड़े हॉस्पिटल के डॉक्टर ने अप्रोच किया कॉल ब्लैडर कैंसर की तो बोला अगर आप नाम पे बना सकते हो हॉस्पिटल बना सकते हो मैंने कहा ये एप्लीकेशन तो हम ये पर इनिशियल मोटिवेशन जरूरी है जितना हो गया ऑनलाइन ठीक है कोई क्वेश्चन और कुछ अगर बाद में भी कुछ क्वेश्चन आते हैं तो ये ईमेल आईडी है या किसी को प्रोजेक्ट में काम करना है पार्ट टाइम मॉनिटर करना है इंटर्न करना है एआई के प्रोजेक्ट को देखना है या स्केल अप प्रोजेक्ट है और उसी तरह से बात करनी है अब हम लोग वो लिंक आ चुका होगा आपके पास ने बोला सबको मिल गया स्लाइड ये मिल गया क्या अब इसका हम लोग वो करते हैं रियल टाइम तो मुझे वो मेल कर दोगे लिंक रावल आप उसी ऑनलाइन देखते रहना क्योंकि ये प्रोग्रामिंग का वो पेज है तो प्रोग्रामिंग के हिसाब से चलेगा बोल नहीं सकते बाय दैट टाइम एक फीडबैक फॉर्म में दे रहा हूँ जरा इसको भर दो जब तक हम ये शुरू कर रहे हैं टाइमी इसको जरा क्लिक कर लो फोन पे या लैपटॉप पे और आज के लेक्चर का फीडबैक आप लिख करें देखना 7 से आएगा या 70 से आएगा देखो नहीं आ रहा 70 का तुम्हें थोड़ा सा समझ आया अब तुम्हें वो कंटेक्स्ट पीसेस का पता लगना शुरू हो जाए समझिए ना रावल ने वेट पे भेजा वो लिंक। तो लैब कोड क्यों भेज दिया? अच्छा, उस बच्चों को तो नहीं भेज दिया लैब कोड व्हाट्सएप पे? नहीं, तो लैब कोड हमारा ही है। सबको स्क्रीन दिख रहा है? सबको स्क्रीन दिख रहा है? तो फर्स्ट डिटेक्ट्रॉन 2 दिख रहा है ट्यूटोरियल? तो हमने शुरू करते हैं इसको। सबसे पहले इंस्टॉल करना है हमने डिटेक्ट्रॉन 2 को। नहीं, पहला जो सेक्शन है इंस्टॉल डिटेक्ट्रॉन 2 प्रो लैब के अंदर, इसमें ये पिप इंस्टॉल नाम की कमांड्स होती हैं, तो वो हम यूज कर रहे हैं, और गिट क्लोन कर रहे हैं और डिस्टिल कर रहे हैं। ये सब मैं रन कर रहा हूँ, देखो इंस्टॉल हो जाएगा वहां। सब लोग अपनी इंस्टॉलेशन शुरू करें उसमें अपने अपने प्रो लैब के। अब हम शुरू करने जा रहे हैं। तो इंस्टॉलेशन हो जाएगी, उसके बाद हमने नेक्स्ट क्या करना है, इंपोर्ट करना है रेलेवेंट लाइब्रेरी को, टॉर्च 2 को इंपोर्ट करना है। तो नेक्स्ट जो कमांड्स है वो है इंपोर्ट करोगे, फिर कूडा को वो करोगे, क्योंकि ये जीपीयू का कोड है, तो कूडा नाम के एक सिस्टम को एक्टिवेट करना होगा। तो CUDA नाम की कुछ कमांड दिखेंगी तुम्हें, फिर उसके बाद तुम लॉगर को सेटअप करोगे, फिर कुछ लाइब्रेरीज डालोगे वहां पर, और फिर कुछ यूटिलिटीज डालोगे। मैं बता रहा हूँ। तो in the chat box, I am typing the link, those people who are online for the tutorial, the collab link. Start that link, click on that link and start working on that.
Now we are going to start with the online presentations. I would like to invite the first candidate, that is Aman Arif. Aman, are you there?
Yes, ma'am.
Yeah, please start your presentation.
I'm just sharing my screen. Is the screen visible?
Yeah, it was, but now it isn't. Share once again.
Yes, ma'am. Just a second. Good afternoon to one and all present here. My name is Aman Arif, BTech Biotechnology student from MET University, Uttar Pradesh, Lucknow campus, India. I am pleased to share with you my research finding that hold the potential to revolutionize dementia detection through application of machine learning. My title is Machine Learning Based Dementia Prediction Using Clinical Data Non-Invasive Approach for Early Detection and Management, exploring into the merge of artificial intelligence and healthcare with focus on technology to enhance the dementia early dementia and personalized care for individual having this complex condition. Moving on to the learning objective. You all able to understand the machine learning in healthcare, learn the step-by-step approach, data collection, pre-processing, model training, evaluation, iterative enrichment, and final prediction. Understanding the algorithms like KNN, XGBoost, etc. for predicting dementia. Recognizing iterative improvement, optimize model accuracy by testing algorithms, feature selection, and parameters. Realize the potential of machine learning for early diagnosis and personalized care. Acknowledging large data set importance in developing reliable machine learning model for clinical practice. Moving on to the introduction. Dementia impair a cognitive function in older people's current diagnostic are very costly and invasive. Machine learning, a branch of AI, learns from data to predict outcome effectively. We analyze a comprehensive data set with imaging and clinical data from 150 individuals ranging age from 60 to 96 using an algorithm KNN XGBoost decision tree support vector machine TensorFlow. We achieve 94.66 accuracy. Applying this in clinical setting could transform dementia screening and care. Procedure that I have taken include data collection, gathering detailed subject ID, MRI ID, group, dementia is present or not, visit, MRI delay, gender, handedness, age, education level, and SES. Feature selection, use stat and correlation and knowledge to pick key features and trim irrelevant and repeated attribute for simple analysis. Data pre-processing, dropping missing or fixing missing values or dropping them. Check for duplicate data, normalize data attributes for fair comparison. Model training, utilize machine learning tools, KNN, XGBoost, SVM decision tree, TensorFlow, training model on proper data set to learn the pattern. Model evaluation, use matrices like mean absolute error, mean standard error, and accuracy. Compare model on separate data set, then iterative improvement. Identify algorithm strength and weaknesses and revisiting features and pre-processing and training it. In nutshell, the process include collection of data, choosing features, pre-processing, training model, evaluating and refining more accurate dementia prediction using machine learning. Some of the literature reviews include from the rich pool of research we gain insight from various studies. For instance, Udin et al. Illuminate the exceptional accuracy of K nearest neighbor model for disease prediction. Ugen Lee et al. Applies the power of extreme boosting for to diagnose chronic kidney disease. Sarika et al. Explore the random forest potential in predicting Alzheimer's transformation with remarkable accuracy. Ding et al. Discuss the new use of semi-supervised support vector machine for incorporating unlabeled data. Jingo et al. Offer a comprehensive overview of decision tree, highlighting their algorithms and accurate classification uses. Ashraf et al. Explore the classification of TensorFlow model in cardiovascular disease prediction, emphasizing the benefit of advanced technique. About the dataset that I have worked on are the OASIS dataset contained record of 373 individual aged from 60 to 96 evaluating dementia. It includes demographic attributes like age, gender, education, and SES, and matrix attributes like MMSC, CDR, ETIV, NWBV, and ASF. We prepare by using unnecessary column, transforming group for binary prediction of dementia, and splitting data into 30%, 80% training and 20% testing. We scale attribute with min-max scaler for fairness and carefully selected features and visualize correlation via heat map analysis. integrating neuroimaging and clinical data, enhance dementia prediction, advancing and early diagnosis and management. Attributes, insights. Gender indicates subject gender, handedness, all subjects are right-handed. Ages in years, education, complete education of subject. Socioeconomic status, categorize socioeconomic position from 1 the highest to the 5 the lowest. Mini mental state examination scores 0 worst to 30 best. Clinical dementia rate, measure dementia severity 0 to 0 none to moderate. Estimate intracranial volume, estimate the total volume inside the brain in mm cubic. Normalize brain volume, express the whole brain volume as a percentage of gray matter and white matter. And Atlas scaling factors, that is unitless and scale factor transform brain skull to Atlas target. In summary, these attributes provide a crucial information for disease prediction of dementia and its assessment. A method that I have taken. My objective was to accurately identify dementia using multi-dimensional dataset. To achieve this, we employ 6 machine learning algorithms for robust outcome. We remarkably were attained an accuracy of approx 94.66 in determining dementia cases. By analyzing this multi-dimensional dataset, we effectively determined dementia. Our target was to achieve the high accuracy and ensemble uh, and, uh, and enabling early and precise dementia diagnosis. Algorithms that I use are k nearest neighbor, support vector machine, random forest, decision tree, gradient boosted algorithm, artificial neural network, TensorFlow, and step-by-step approach that I have taken include data collection, feature selection, data pre-processing, model training, model evaluation, iterative improvement, and final prediction. In essence, our method combine diverse machine learning technology with comprehensive steps for accurate dementia detection using multi-dimensional dataset. Starting with first, that is k nearest neighbor. The k nearest neighbor is an algorithm calculate the Euclidean distance between the training and the new data set. It then select the top k data points with smallest distance. This is done by GUI value from data training and HI value from new data set. Making decision is based on the labels of k nearest neighbor, and final prediction is determined by the most frequent label among these neighbor. In summary, KNN classified data by measuring data and choosing the label of nearest neighbor for accurate precision. On the screen, there is a code snippet for the implementation of k nearest neighbor. Moving on to the next is random forest. The ensemble technique of random forest combined decision tree to boost the accuracy. It provides an overfitting by avoiding overly fit model to train dataset. It generates a multiple subset from the training dataset using a bootstrap method and train the individual trees on these different dataset. The output are then merged through averaging or voting to make the final prediction. This approach enhances the model performance on the new and unseen dataset. In essence, the random forest emerge decision tree, reducing overfitting and chance accuracy and generalization. On the screen, there is a code snippet for implementation of random forest. Moving on, next is artificial neural network, TensorFlow model. Neurons values are initially set randomly, and then activation transmit information to produce output. Through multiple training epochs, the model refine itself into dataset to fine-tune parameters. Visual aids such as loss and accuracy curve and network structure diagram enhance the comprehension. The neural network architect consists of 4 layers with 128, and 64 one neurons. It employs binary cross entropy loss function and Adam optimizer. The model is trained for 300 epochs for normalized data is powered by TensorFlow. and achieving an impressive accuracy of 94.66 in dementia detection. On the screen, there is a code snippet for the implementation of ANN TensorFlow model. Next is Extreme Boost. Extreme gradient boosting is a potential machine learning technique, yeah, algorithm. It progressively add trees to enhance the accuracy. It excel in handling integrate data and include multi-dimensional data set. To prevent overfitting, it utilizes L1 and L2 regularization. The commonly used implementation is XGB classifier from the XGBoost library. It trained on the normalized data and test on separate data, and achieving an accuracy of 89.33% in dementia prediction. In summary, XGBoost improve accuracy by iteratively combining trees and making it suitable for complex data analysis like multi-dimensional data set and achieving a high accuracy in dementia prediction. On your screen, there is a code snippet for implementation of XGBoost. Next is support vector machine. We employ support vector machine for precise dementia detection. SVM aim to maximize the margin between the support vector and the decision boundary. This approach enhances the model ability to handle unseen data and outliner effectively. In achieve an accuracy of 88 in predicting dementia cases using SVM. Its strength in managing multidimensional data set further improved accuracy. In summary, SVM efficiently predict dementia by maximizing the margin and effectively handle multidimensional data set, resulting in significant accuracy enhancement. On your screen, there is a code snippet for the implementation of support vector machine. Last but not the least is decision tree classifier. I use decision tree classifier for precise dementia detection. We appreciate its simple and easy understandable nature. The algorithm employ recursive data splitting based on the feature value to create a decision tree, and resulting tree structure was valuable in identifying crucial classification feature. We implement the algorithm using scikit-learn's decision tree classifier, fine-tuning the parameters such as max underscore depth and min underscore split. The outcome was 88% accuracy in predicting dementia cases. In conclusion, decision tree classifier approved effective in predicting dementia due to its simplicity and it is for complex multi-dimensional dataset scenarios. On your screen, there is a code snippet for implementation of decision tree classifier. For model evaluation, we assess 6 machine learning algorithms: KNN, random forest, support vector machine, decision tree, XGBoost, and ANN TensorFlow. The outcome was impressive of approx 95% accuracy in predicting dementia. Our evaluation include a range of matrices such as F1 score, precision, recall, and confusion matrix. Precision estimate the accuracy of positive prediction, while recall measure the proportion of correctly predicted positive values. The F1 score provides a balanced measure of precision and recall, and accuracy reflect the overall correctness of the prediction. In summary, the use of diverse evaluation metrics confirm the accuracy of multiple models in effective prediction of dementia cases. Detailed insight of model performance. It involves utilization of confusion matrix with display matrix such as positive, true negative, false positive, false negative for each model. As we validate our approach, we find that the model shows strength in robust and high accuracy of dementia detection. The positive matrices further support the efficiency of our model approach. In summary, by analyzing the confusion matrix and validating our approach, we underline the model's solid performance and showcase the potential impact and positive outcome of our approach. In conclusion of my presentation, the model that I have made by KNN, XGBoost, and random forest, support vector machine, decision tree, and TensorFlow uses using these algorithms demonstrate an high accuracy of 94.66% in dementia detection. Robust performance suggests a potential for early diagnostic and personalized care. Comprehensive
Aman,
assessment. Yes, ma'am.
Aman, your time limit was of 12:15 only.
Yes, ma'am.
So
It
can
is.
you wind this up fast?
This is the conclusion only. I am just explaining the points that I have written on the PPT. Just 2 minutes. It is fine. I can take 2 minutes.
Yeah, sure.
Okay, thank you. Comprehensive assessment use F1 a robust performance suggests a potential for early diagnosis and personalized care. Comprehensive assessment use F1 score precision recall confusion matrix. Result validate impact on dementia detection and healthcare. Future exploration include ensemble method, feature engineering, fine tuning, machine learning, enhance early diagnosis detection for better outcome and quality of life. In summary, the research highlight the power of machine learning in advancing dementia diagnosis, benefiting patient life and healthcare as whole. These all are the references that I have taken from. Thank you.
Thank you so much, Aman. Now I would like to invite Anand Krishna. Are you there? Anand, are you there? I guess he's not there. So we'll move on with Siddharth Yadav. Siddharth, are you there?
Yes, ma'am. Am I audible?
Yes, you are. Now
Okay,
I
ma'am.
would like to invite you for your presentation.
I'll just share my screen.
जो टॉपिक्स का इमेजिंग का ही था ना,
Yes.
बेनिफिट्स ऑफ इमेजिंग।
Yes. Ma'am, is everyone able to see my screen? Can you please confirm?
Yes, yes.
Okay. So, hello everyone. Myself Siddharth Yadav, and I will be taking this presentation on pictures that lie, or detecting scientific image manipulation. So let me just tell you a little bit about myself. My name is Siddharth Yadav. I'm a PhD scholar from Amity Institute of Biotechnology. I'm currently working in novel peptide synthesis, and my major interests are optimizing machine learning DL models and image processing, computer vision, and anomaly detection. You can find me on GitHub and also on LinkedIn. So now, since this is about scientific imaging, let's talk about a time before images. So before photography actually became common, scientific literature was mainly composed of handwritten illustrations. Like you can see here, this is a kraken or a fish, and also retina, the image of the cell layers of the retina. But after the advent of photography, a lot of the scientific literature was introduced, a lot of images were introduced into scientific literature, and a lot of scientific breakthroughs actually were perpetrated as images themselves. So we can see photo 51. It was the first time the double helical structure of DNA was discovered by Rosalind Franklin. Another one is the positron cloud chamber image by Carl Anderson. This was the first ever proof of antimatter. So these are a lot of big breakthrough scientific discoveries that took place, which actually signify the importance of images in not just being supplementary to the material, but actually being the result themselves. So a lot of images today, so I've taken specific examples from medical imaging and life science domain. So a lot of images we can see things like the Western blot bands or PET scan, CT scan, MRI, and also a lot of fluorescent imaging techniques. So lots of varied types of images are actually present today. But just one key question, something that deviates from the general overview of all the presentations and the conference in general is, are the images authentic, or can the images be trusted by themselves? Just for example, this is a very common manipulation that you can perform. So this is basically forging a Western blot band, and this is just another image, a way to manipulate the images. So this is known as copy move forgery. And basically scientific literature, a lot of examples can be found of such forgeries. So for example, these two are original images, but we can take one part of an original image and put it in the other one, adjust for contrast, brightness, and hue, and we have another forged image. This type of forgery is known as splicing forgery, which is also pretty common in scientific literature, or known as in fraudulent cases, that is. Finally, another very sneaky form of forgery could be known as image reuse forgery. So over here, you can see on the left, there's this paper which was published in 2015, which says that this image is actually a disease-affected liver cells due to excessive alcohol abuse. And paper B in 2019 is taking just a negative black and white photograph of the same image and claiming that to be invasive lung cancer cells affecting healthy tissue. So this is basically a misattribution or reuse of the image. This is known as image reuse forgery. So the answer that the images can be trusted, no, not all images can be trusted. So what are the implications of image manipulation? So firstly, it is deliberate deception and fraud, misallocation of research funds, and propagation of unfounded methods. But the most critical, I believe, drawback of image manipulation is that it hurts scientific integrity. It basically undermines all the purpose behind whatever research that is committed and is involved inside the forgery. But not all is gloomy. We can actually detect a lot of these forgeries. So let's talk about the detection of these forgeries. Let's look at the copy move forgery detection first. So these are just three basic categories. There are several subcategories, subtypes. Some of the forgeries might be more sophisticated also. But these are just the three illustrative examples I have chosen to demonstrate that such a field actually exists, and active research is being done in this field. So let's look at copy move forgery. So this is an original image. So I've taken a band and I've just replicated that band onto panel number 3. So this is the manipulated image, and from the human eye, it doesn't actually look manipulated at all. You can't actually look about a lot of variations, because even in a real Western blot image, many of the bands can have very similar appearances. So in this manipulated image, how do we detect it? So one common way would be to divide the images into several blocks of pixels. Then we compare each block to every other block of the pixels. And then we try to find out blocks which are very similar to each other or with high degree of similarity. That way we can understand what types of blocks are actually correlated to each other. So that way we can try to solve copy move forgery, but it's not really that simple. So because pixel to pixel comparisons don't work. And what do I mean by that is, so let's say this was the band that I actually copied over to the next panel. I can actually apply different transforms to it before actually copying it. So it would be scaling. So I'm increasing or decreasing the size of the band. I can rotate the band. I can skew the band. I can also add some noise to the band. So all these things actually change the pixel density, pixel distribution, brightness, and all these characteristics. So just a pixel to pixel block comparison doesn't work. So what is the need? What do we have to do? We have to describe the pixels without being affected by the transforms of the pixels. So one way to do that, there are actually many ways, but one way to do that would be to use something called Zernick moment, or basically it's a mathematical representation of a pixel or a group of pixels. So this is these are the equations required to calculate the Zernick moment. So this is the mathematical representation of all the different pixels, and this is of Zernick order 4. So Z4, that is the Zernick order 4 that we're looking at. So basically, Zernick moments give you a vector of different numbers or numerical vector, And you can see that the original one has the numbers in green, orange, and blue. These numerics are very similar to the other ones. So even though the transform is being applied, these numbers don't change a lot. You can see they're basically off by, let's say, 0.1 only. So Zadnik movements are able to capture the essence of the block, and it does not, if they are not affected by a lot of these transformations such as scaling, rotation, and noise addition. So in that way, we can actually understand what type of block is being copied. So we don't have to rely on pixel to pixel comparisons. Towards this is a paper published in 2020, but it was retracted because a lot of these bands are actually basically copied with each other. So these are the instances of a lot of bands. So this is all forged images. So all of these bands are forged. For example, these two orange bands are actually just rotated and pasted together. So a lot of these things are able to be detected now because of such methods. Let's talk about splicing forgery real quick. So this was actually the image that was not belonging to the original image. So it was copied and pasted from somewhere else. What we can do to identify that is we can't use any copy move because it's not a part of this image either way. So what we can actually do is actually, because both these images were actually taken from different photographs. So different photographs can also have different noise patterns. What do I mean by that is this is just a very quick go through. So generally when an image is generated, you have a lens, you have an image sensor, then you have a lot of post processing going on after the image has been taken. So a lot of these operations, like the lens, we can have the spherical or cylindrical, also known as optical aberrations. In the sensor, we can have a lot of fluctuations, photovoltaic fluctuations, and the processing pipeline can be unique for different manufacturers. For example, a Canon camera will process the image slightly differently to a Nikon camera. So a lot of these changes actually change the underlying noise pattern. So when we try to convert the image and extract the noise, we can clearly see a patch appear, whose noise distribution is very different from the rest of the image. In this way, we can understand that this difference in the underlying noise pattern can help us detect splicing forgery. Now let's look at the most difficult type of forgery to detect, because it's not exactly a forgery, it is reuse. So like I said before, this was a paper in 2015, and on the right you can see a paper in 2019, and both of these images are actually the same, but the paper in 2019 has basically reused that image. So there's no forgery, there's no copy move, there's no splicing, but just reuse of that image. So how can scientists or publishing companies actually find this type of forgery or abuse? So what we can do is whatever your query image is, and this is something that is being actively done. So we can try to find a query embedding or image embedding. Image embedding is basically a representation of an image by a neural network. So a lot of this auto encoder or encoder decoder architectures are able to get a lot of this represent the image into a query or an embedding. So we can generate a query embedding for this, and we have large repositories of scientific documents. We can extract billions of images from them and create image embeddings for each of these images. Now, with this large image embedding library, we can perform a lot of indexing and search algorithm optimizations with stuff like KD trees, LSH, approximate nearest neighbors methods. So what they will do is they will create an index of all these embeddings, which is like essentially sorting and making a different graph structure out of this particular thing. And then we can actually compare this billions of images and the embeddings with the query embedding, and we can have a similarity calculation. So the closer the images, the higher the value of the similarity calculation that there will be. Now we can find a set of images which are having extremely similar or very high similarity calculation, and then we can pull out those images, and then we can understand that okay, this query image was actually taken from a 2015 research article or a research paper, and this has actually led to the retraction of this paper in 2019. Now towards the conclusions, well, image manipulation is the most prevalent form of deliberate scientific misconduct. Just in the year 2020, 5,000 different cases of image misconduct were documented in literature, and a lot of them had to do with the splicing and copy move forgeries and even image reuse that I just showed you. Forgery detection techniques are continuously improving due to advances in AI. So this is an active field, and a lot of researchers are contributing towards this field for detection of forgery in scientific domain, even in other domains such as insurance and digital authenticity, and to stop the misinformation spread. This has resulted in high retraction rates and significant reduction of fraudulent literature. So the researchers can no longer rely on simple Photoshop techniques just to make up an image and produce false results. So because a lot of the publishing houses like Nature, Elsevier, Springer, and they're actually using a lot of these scientific systems to detect this type of fraud. So that's that. But the major key conclusion that I would like people to take away from here is that under no circumstance should you actually compromise your scientific integrity, because that actually goes against the fundamental nature of science itself, which is to experiment and research for the truth itself. Thank you very much. If anybody has some questions, they can put it in the chat box. Otherwise, thank you very much for listening and being patient.
Thank you so much, Siddharth. Now I would like to invite Keshav Mittal for the next presentation. Keshav, are you there?
I'm there. Yes, I'm there. Am I audible?
Yeah, you are.
Okay, 1 second. And just share the screen. Is my screen visible to everyone?
Yes.
Okay. So, respected faculty members, esteemed colleagues, and honored guests, good afternoon to everyone. I'm Keshav Mittal, a student at MIT Institute of Biotechnology, pursuing BTech in Bioinformatics. I'm delighted to welcome you all to today's presentation on a topic of immense significance in the field of medical science, which is breast cancer medical imaging detection and analysis. In a world where healthcare is advancing at an unprecedented pace, it is imperative that we stay at the forefront of innovations that aid in the early detection and accurate analysis of diseases, particularly ones as prevalent and potentially devastating as breast cancer. Now, the following presentation or research is basically divided into 4 sections. On first, we have introduction to breast cancer, where the basic knowledge of the same will be provided. Up next, we have exploratory data analysis, which is considered a critical component of every research for better understanding of the data and its variation. It will then be followed by CNN architecture and methodology for predictive analysis, where we will discuss the deep learning model working and outcomes. Finally, it will be summed up by the results obtained from a learning model and conclusion. Moving forward, we have introduction to breast cancer. In this section, we will paint a comprehensive picture of what breast cancer is and its prevalence in today's world and the impact it has on individuals and societies. Here on the side, we have a short description of breast cancer and how it spread it is across the globe. As we can see, breast cancer occurs in every country of the world approximately. So now the question arises is, what is the use of ML or AI in cancer detection or analysis? Well, treating breast cancer using medical imaging and machine learning holds the potential to significantly enhance the effectiveness of diagnosis and monitoring. Here are some compelling reasons why this technology should be integrated into breast cancer care, like the early detection, improved accuracy, treatment planning, predictive modeling, reduced human error, and large-scale data analysis. Now that we have established a solid understanding of what breast cancer entails, let us delve deeper into the realm of medical data that forms the basis of our analysis. On our journey through exploratory data analysis, seeks to uncover insights hidden within the intricate patterns of breast cancer data. In this section, we will navigate through the information-rich landscape of medical data, extracting meaningful trends and preparing the groundwork for our subsequent discussions on medical imaging techniques. Exploratory data analysis. It is a preliminary and crucial phase in data analysis where you interact with and visually summarize the data set to understand its main features, patterns, and potential issues. The primary objective of EDA is to uncover insights and formulate hypotheses that further guide analysis or modeling. Up next, we have some details about the dataset on which we performed the data analysis. Like the dataset was imported from UWCS FTP server which was entitled as the Breast Cancer Diagnostic Data, and it comprised of 30 real valued features, which were computed for each of the image. And in the class distribution, we have 357 benign and 212 malignant images. The value of the diagnosis column were transformed into the B's benign as 0 and malignant as 1 for the binary search. The variation of the attributes, sorry, all these and these some of the libraries which were used to generate the plots for in-depth understanding of the data. These were the libraries: Seaborn, sklearn, NumPy, Pandas, Matplotlib, and IPython. Next, we have pair plots from the variation of the attributes in the entire data set were obtained through Matplotlib, whose results can be seen here. This was for concavity mean, fractal dimension. Then we had for texture, area, and smoothness. It was calculated for all the 30 real valued features. Next up, we have pair plots using Seaborn. Pair plots graph were made using Seaborn library to see individual relationships between feature and diagnostics. They are particularly useful for understanding the relationship and distribution between multiple numerical variables simultaneously. Moving forward, we have visualizing data with Valiant plots. It is a type of data visualization that combines aspects of a box plot and a kernel density plot. It is particularly useful for understanding the distribution of a continuous variable or comparing distributions between different categories. And for all the 30 features, it was calculated. For the box plots, they are used as an alternative for violent plots. Box plots are also useful in terms of seeing outlines. So this is just another way of data visualization. Next up, we have swarm plots. They are another type of data visualizing technique that help you to see the density of data points and any potential patterns or clusters within categories. The last visualization which we have is heat map, which is graphical representation of data where individual values within a matrix are represented as colors. Heat maps are particularly used for visualizing complex data set patterns and relationships. The colors in the heat map indicate the relative magnitude of the values, allowing for quick identification of trends and patterns. Having gained valuable insights through exploratory data analysis, the focus now shifts to leveraging advanced techniques for addressing critical challenges in the medical field. Specifically, the subsequent section delves into a crucial application: breast cancer segmentation or detection using convolutional neural networks. As we transition into this technology, we will explore the methodologies and advancement that underpin the development of CNN-based models tailored for medical image analysis. If we see about the data set, it has been imported from Kaggle, and the link for the same has been given here. We can see the data as it comprises of ultrasound images of 600 patients, and other key information has been shared in the slide. Up next, we have a small example of how the raw data set looks. As you can see, we have your benign, malignant, and normal ultrasound scans. Now, just to give you a brief about CNN, it stands for convolutional neural network, and it is a type of artificial neural network designed specifically for processing and analyzing grid-like data, such as images and other multi-dimensional data. They are particularly well suited for medical imaging due to their ability to automatically learn and extract features from the images. Next, we have the objective. So it was for the development of a convolutional neural network for the project that will be able to spot tumors in the ultrasound captured photos of patients, attempting to create a segmentation model that is incredibly effective and can identify the cancer region. Initially, all the medical images were used, no matter it was malignant, benign, or without cancer. The strategy was for the strategy, we have the unit structure was used in addition to make the neural network predict the types of cancer that it selects. On the other hand, data augmentation was used to make each medical image darker or lighter in order to avoid having the neural network focus only on the dark area in the photographs. So this is how the data augmentation works. For each image, as you can see, we have 3 images. One is a bit dark and the other is quite light. This helps in the image detection for the model. The methodology involved in the building involved in building the model started with data augmentation, after which data splitting was performed and the data set was split into test and train and validation. The validation set is used to tune hyperparameters and the test set assesses the model's final performance. To felicitate the discovery of the cancer region in the medical images, the MSE loss function was used to determine the two types of cancer, which makes the loss function derivable and continuous at any moment, which felicitates the training process and makes the neural network able to find the link between the tumor area and its shape with the two types of cancer tumor. Finally, after building the model, it was run over the training dataset with an epoch count of 20. For the final, and this was the trained data which we used. For the final results, we have the use of MSE loss function in determining the type of cancer tumor that had the best performance in achieving stable training between the segmentation process and the process of determining the type of cancer tumor. Precision recall curve showed a positive trade-off between accuracy and recall, highlighting the model's ability to accurately detect malignant instances. The model exhibited a loss of 4.4002, whereas the unit loss and label loss came out to be 0.0304 and 1.4806 respectively. With a confirmed accuracy score of 94.58%, the deep learning model offers an appealing strategy for precise breast cancer detection. Here we have some of the graphical representation of the performance of a model and other matrices for validation data, which can be seen here. The accuracy score, prediction, precision scores, recall, F1, and all the other validation sets. At last, we have the visual representation of a detection model, which is demonstrated through some of examples from the results. And this can be seen. Let me show this to you. As you can see for image, this was the raw image, and for that we have an original mask and the predicted mask. And this was calculated for all the data set. Ending the presentation, I would like to say this research has shed light on the pivotal role of advanced machine learning techniques in revolutionizing the field of medical diagnostics. The utilization of CNNs coupled with meticulous EDA enables us to accurately identify and delineate regions of interest within medical images, contributing significantly to early disease detection, precise treatment planning, and improved patient outcomes. Finally, I would like to extend my heartfelt gratitude to our esteemed faculty members, Dr. Abhishek Sen Gupta and Dr. Priyanka Narath, for their firm guidance, invaluable insights, and motivating spirit throughout the journey of crafting this research paper. Their contributions have truly enriched the quality and depth of the work, and I'm genuinely thankful for the privilege of working under such exceptional mentors. Thank you all.
Thank you so much, Keshav. We wind up with the session here. I would request all the participants to be seated at 1:45 at F3 auditorium. We look forward to you. Thank you so much for joining. This session is over now.